Hello everyone, and welcome to this year's virtual SDC. My name is Neil Wordmuller, and I work for ARM, and I'm based in Cambridge in the UK.
Hello everyone, my name is Jason Mulgard. I'm a Storage Solutions Architect at ARM, and I work very closely with Neil on storage architectures at ARM. I'm based in the US, and I'm very happy to be speaking with you today.
Great, so let me share my screen, and then we can begin the presentation. Great, so today, Jason and I are going to talk to you about flexible computational storage architectures. And with the agenda, really we're going to first of all cover what's driving computational storage, why is it important, why are people getting involved in it, why is it moving forward, and where do we think it's going. We're then going to talk about what are the controller architecture options. Obviously, there are many different ways of implementing computational storage, and we'll talk through a few of those different options, primarily from a hardware perspective. But also, we see that Linux is a very important basis for computational storage. So we'll talk about what's driving that adoption of Linux for computational storage, and then we'll talk a bit about the key Linux workloads that we think are very, very important for that. And of course, we'll finish up with some conclusions from our talk. So what is driving computational storage? So we see that computation is moving to storage. There's been quite rapid adoption across the industry and standardization that's being developed. But the reason behind this, so moving the computation to where the data is stored, is primarily driven by these key factors. Obviously, if you're moving data that's stored to a server to process it, be that in the same data center or even remote, it takes a lot of bandwidth. And that's especially true when you get into images and video content, but also the huge amounts of information being generated by the Internet of Things. And obviously that data movement also consumes power or energy for that movement, which as you shift it across through that fabric, it takes power every time it's copied and moved. Also, the cost of all this movement, the cost of the energy has a big impact on this. And obviously moving these huge files takes time. It adds latency to the whole system. So computational storage really reduces the latency because you only have to move the data from where it's into the storage device from either the NAND that's in the drive or even the spinning disks if it's a hard disk drive. Also very reliable because it's very distributed system. It's also much less data movement. And that reduced data movement also increases security. By moving less data across networks, increases the security. If you're just returning results and not moving huge files or databases, then the security of that data is increased. So to give you a very brief overview, computational storage, it's about generating insight where the data is stored. So the traditional model in the picture here on the left, it's all about basically the compute servers probably make a request for the data to the storage. The storage retrieves it in SSD from the NAND, it moves it into the DRAM on that system, then it packages it up in protocols, so NVMe normally, and then PCIe often to move it, or NVMe over fabric if going over something like an Ethernet transport with NVMe over fabric TCP. But that data then's got to move all the way to the server, to the compute, which can then actually do the compute on it. But that obviously is inefficient in terms of energy. It increased latency. The compute, the servers are often sitting there waiting for the data to be available to continue their computation with. As I said before as well, that security of moving all of that data really gives it a wider attack surface. But moving to computational storage, really this is where the compute happens directly on the drive. So the server in this picture will make potentially request an operation. The computational storage drive will retrieve it from the NAND or the spinning disk into its own memory and then compute it directly there. It doesn't have to wrap it up in protocols and move it anywhere, and potentially return the results. The other aspect is that compute in this diagram in the middle picture can also happen autonomously. So it could just be the data's being stored to this drive, and then in the background, the compute can work on it and then just return results. So it doesn't necessarily have to be invoked by a server. It can just work autonomously. And I think there are a lot of applications for that. And it's really about, yeah, these data-centric workloads. So in order for computational storage to take off, ARM and many other people in the industry think that computational storage really needs a standard. So with SNIA, there's the Computational Storage Technical Working Group, and that's driving a standard to enable the big customers of computational storage to have multi-sourcing. They can buy computational storage drives from many different suppliers. ARM is a founding member of this technical working group. There is a draft standard available today. It's 0.5R1, and looking to basically move that standard forward throughout the remainder of this calendar year. They do take time to be developed and approved, but yeah, things are moving fast, so we do expect to see this standardized fairly shortly. And you can see in the diagram as well, there are two main areas where the compute can happen. One is sort of above the storage, so the computational storage is communicating to a number of storage controllers that are beneath it, and SSDs in this case. The other case on the right-hand side is where you have the compute actually on each computational storage drive, so within the drive itself. And that has some advantages of scalability. If you add more storage, you automatically add more compute. Some of the earlier computational storage drives that are out in the market today have been using FPGAs. Now the FPGAs, I think, are a good solution to get proof of concept products to market quickly, but certainly we're seeing a number of those partners now moving quickly to developing their own chip to an ASIC, which is lower power and lower cost, but also very importantly, it's much easier to program. FPGAs are fairly complex to program, but very high performance. So there are balances, and FPGAs will exist in computational storage in the future, but as will ASICs as well. So I won't dwell on this slide, but obviously it's a big industry initiative for computational storage. Within SNIA, there are 44 participating companies, all of the big names that you'd expect to see in this area. So yeah, they're all working very closely together to produce this standard and enable everyone to produce interoperable computational storage drives. So I think as the standard matures, what people will do is the most likely outcome that's being worked towards is that there will be extensions to the NVMe protocol, so the non-volatile memory express, to enable you to deliver the computational storage, to enable the discovery, configuration, and usage of the computational storage that's now on the drive. So in the top diagram here are really showing that in a standard PCIe SSD, what people are doing is going to basically be adding in these new computational storage protocols to that drive. What's also important, I think, as well, is that there's a big movement towards NVMe-over Fabric, and certainly a lot of interest in the Ethernet version, so NVMe-over Fabric TCP. And this is basically just encapsulating NVMe packets and moving them across whichever fabric, but in this case I'm demonstrating it with Ethernet, so that actually this drive can now be remote and just networked up to whatever the server is that's managing it, and could be very long distance or right at the edge of the whole network that this is attached to. And obviously, once we've got the new SNIA computational storage NVMe protocols, they'll just be encapsulated in the same way as any other NVMe over Fabric packet. But what we think is really exciting is extending this with on-drive Linux. So basically, you've got an Ethernet interface now to this SSD, but if you put Linux on that drive, it opens up a number of possibilities. So you can use it as a completely standard SNIA standard computational storage drive, but also by having this TCP/IP link to a Linux processor. standard TCP packets can also be sent to this, and that enables you basically to very quickly network up this into standard switches that are very low cost. And on the drive, you can run any standard Linux distribution. And basically, you can use all of the systems that you would be using today to deploy workloads, so Kubernetes, Docker, or many of the other systems. It basically just starts looking like any other piece of server equipment in the whole system. But very key to this, and actually Jason will talk a bit more about this in a bit later in the presentation, but Linux actually understands the file system. An NVMe drive just understands blocks of data that's been given to store. Typically, it'll break it up into smaller parts and store them in the pages of the NAND and retrieve them on request. But it doesn't know that a JPEG's made up of 10 blocks. It just gets 10 blocks. It doesn't know what they are. So actually doing anything intelligent with that data on the drive in computational storage in an autonomous way is very, very difficult unless you've got an understanding of that file system and what's actually being stored on the drive. Having Linux enables you to mount that file system, enables you to do that, get that understanding and work more autonomously. So, and again, the security, it's basically all comes as standard in this kind of system, because whatever the security you're using in other Linux boxes, you can use exactly the same security now on these computational storage drives. So we see that as very, very key to enabling these systems, in being able to move workloads directly from a server down to the data where it's stored. I think we all know about the explosion of data that's being created in the internet by all the different applications, but also images and video. But that's also seeing an explosion of workloads. So the servers are having to cope with multitude of workloads now that's becoming very, very difficult to manage. In this situation with a computational storage drive, we see some value that whatever data is being stored on that drive, you can have the workloads that are applicable to that data actually on the drive with it. So instead of having to have a server that manages everything, here you can have specific loads that are directly suited to the data that's stored, be it a database, be it video, or whatever other data that you're storing on that drive. So I'm going to hand over to my colleague, Jason.
All right. Yeah, we're going to kind of, as our next topic here, discuss controller architecture options. So next slide, please. So looking at a traditional SSD today, there's already a lot of compute in that drive. So typically it's broken up into a front end and a back end, where the front end CPU manages host interface and FTL, the flash translation layer. This is oftentimes a Cortex-R today, an ARM Cortex-R, or possibly an ARM Cortex-A series. And then the back end is, there's a CPU that is involved in setting up the transfers to the flash and managing those transfers. And frequently this is a Cortex-R, sometimes a Cortex-M series. But of course, the SSD contains lots of built-in accelerators, encryption, LDPC, compression. You could have ARM Neon, which is the SIMD instructions to accelerate machine learning workloads. Some people might have an FPGA, but one thing is definitely certain, all these drives have a lot of DRAM, to the tune of 1 GB per 1 TB of flash, significant amount of DRAM. And some of these storage capacities on these drives are obviously continuing to grow, 16, 32, 64 terabytes. That obviously translates to 16, 32, or 64 gigabytes of DRAM. And just to kind of round out the picture on the overall SSD, of course, there's a PCIe interface that's most common today, running NVMe, SAS to a lesser degree, and SATA is kind of waning at this point. Next slide. So all of this compute on the drive is largely autonomous in the way that it behaves. So the host sends logical block addresses, LBAs, to the drive, and the drive maps those LBAs to a physical block address in the FTL. and therefore determines where the data should be stored on a write or where it could be read from. But this same structure stores the file system that the host operating system uses to map those LBAs into a file. As we know, multiple LBAs are typically needed to create any one file, and the file system keeps track of those LBAs needed to reconstruct that file. So as Neil mentioned, if you've got a computational storage drive that's running Linux on it, that Linux can mount the file system that's stored on itself and make sense of the files that are there and perform accesses on them and operate on those files in the same way that the host would. And so that essentially enables any workload that could be done on the host can now be performed on the drive. And of course, as Neil mentioned, you can do that as the data is being stored in line autonomously, or you can do it after the fact. After the data has been stored, you can deploy a workload to the drive and do some compute in place at any point in time. So next slide, please. So how do you get Linux on the drive? Well, there's kind of three options that we can explore here. So looking at the diagrams on the right-hand side, the first diagram, the top diagram, kind of shows what could be done today using an existing SSD controller and a little daughter card that implements an applications processor. So this applications processor daughter card would communicate to the SSD using the PCIe interface that's existing on the drive today. You move the data off of the controller into the applications processor, perform that compute, and move it back. And obviously there's some issues with this approach. This is probably a great proof of concept, a great way to get started, but you still have to wrap the data up in a PCIe protocol, move it over to the daughter card, unwrap it, and vice versa for anything that you want to send back. There's a physical footprint issue where it's physically larger to have this daughter card, and maybe it has extra DRAM that it needs on the daughter card that wouldn't be needed if it could somehow share everything in the drive. Well, so then that takes us to the next logical progression. If we look at the middle diagram on the right-hand side, where we just take that applications processor and we integrate it in with the controller in the same SoC. So we've eliminated some of the shortcomings of the proof of concept on the first diagram, where we no longer have to wrap up the data in protocol to move it back and forth. We've eliminated that latency, that bandwidth usage by removing that whole interface. And now it's potentially sharing DRAM as well, and that certainly helps with the overall DRAM footprint, and then certainly the overall physical footprint of the drive can be smaller because we don't have that daughter card. Well, then the next logical progression, if we look at the bottom picture on the right, is to combine the applications and front-end processors into the same cluster, where you've got a cluster of processors that are handling both the compute and the flash translation layer. And ideally, what we want is the flexibility to go back and forth, because we don't really know how many we need up front necessarily for managing the compute or managing the FTL. So you may be thinking, well, you know, Linux is still kind of large. Well, yeah, it certainly can be, but actually there are some very small versions that can be easily pared down and downloaded to the drive and installed on the drive. So using one example, Debian 9 Buster provides requirements for as little as 120 megabytes of RAM, maybe, you know, preferably more like 512. And a little bit of storage, 2 gigabytes. We've got lots of storage. We just mentioned, you know, 16, 32, 64 terabytes of storage. And subsequently 16, 32, and 64 gigabytes of RAM. So the system can potentially leverage some of that RAM. I understand also that a lot of that RAM is allocated in the drives and needs to be used for the FTL. So I suppose in worst case scenario, we're talking less than 5% increase to add a little bit of additional RAM to run the Linux in that drive, and over the DRAM that's already there. So as we mentioned, 16 terabyte drive, needing 16 gigabytes of DRAM, you know, maybe we want to have 16.5. That's obviously non-trivial, but not a very large amount in the grand scheme of things. So next slide, please. So what are the keys on that applications processor? Well, certainly to actually have an applications processor that will run Linux, it needs to have a memory management unit, an MMU, to virtualize memory. So ARM has a number of Cortex-A series processors, 21 of them available now, and a strong roadmap. There's more coming. So all those A series processors can run Linux and achieve that at various performance points. And of course, the real key when putting applications processor in your SSD is fitting within the power envelope of the drive and the power envelope of the interface that it's connected to the host. And so there's a wide array of ARM CPUs that are available that are at various performance points and subsequently the lowest possible power for that performance point to be integrated into the design and hopefully meet the power envelope that is required of that design. So some SSD controllers already use an applications processor, as I mentioned at the beginning. Some of them are using that for the FTL. Others maybe need to add one in that are using a real-time processor today. The integration is very straightforward and can easily be added. So a lot of these ARM Cortex-A series processors, in fact, most all of them have ARM Neon, which helps, well, first of all, the ARM Neon is a single instruction, multiple data type of instructions that can be used to accelerate machine learning workloads. So certainly machine learning is a very interesting topic as one of the workloads to run on a computational storage drive, and having that built into the applications processor is potentially very useful. But other IP can be integrated, including a dedicated ML processor. You could certainly have an FPGA, an image signal processor, or other dedicated hardware to implement any kind of computational storage drive. So next slide, please. So to truly achieve that diagram, the third diagram that where you have a combined applications and front-end processor, you need the ARM Cortex-R82. This is a recently announced new processor from ARM, specifically targeted at storage. It is a 64-bit Cortex-R real-time processor with a large address map for high-capacity drives so that you can flatly address your 16 or 32 gigabytes of DRAM and all the other peripherals in your system, and has all the hard real-time that's expected and needed to implement that FTL and overall drive control. But it contains a memory management unit, which allows you to run Linux on this drive or on this core. Of course, there's other features that can help with computational storage drives. So certainly shared coherency across the memory system, and you can even have coherency across to other clusters of Cortex-R82 or Cortex-A in the same system. Or you can have coherency across CXL and C6. And of course, CXL is starting to gain a lot of interest in the storage industry. And it has the Neon machine learning instructions that I mentioned to accelerate machine learning workloads. So if we move to the next slide, we'll get into a little bit more information here about the R82 and how it can run Linux and real-time on the same system. So there's really kind of a couple of different approaches. So the first one is that you could have one core or a single core running both Linux and real-time. And the way that's achieved in the Cortex-R82 is you'd have a real-time hypervisor running at the highest exception level, which can then launch a real-time and an MMU or Linux-based virtual machine at the next exception level. If Linux is executing and a real-time event occurs, it can cause an interrupt. The hypervisor can transition execution from the Linux over to the real-time virtual machine, service that real-time event, and then resume execution back on Linux when it is completed. And the configuration of the MPU and MMU is very simplified in order to help make that context switched in as few cycles as possible. So that's really interesting, and I think it will provide a lot of great opportunities in the future. I think some of the initial development is going to be where users take the Cortex-R82 and they allocate a certain number of cores specifically for real-time and some number of cores for Linux. That's certainly a perfectly valid way to approach it. Either way, the great news is that you can create one controller, and with that controller you can develop multiple products. So for example, you could have one controller that is designed where all the Cortex-R82 cores are running in real time, and it's managing the FTL for an ordinary conventional SSD. Or you could take that same controller and use half of the cores for real time and half the cores for running Linux and computational storage, and run that Linux to do the compute right directly on the drive. So clearly this is going to reduce the number of high-cost mask sets if you're able to leverage that controller across multiple different products. So next slide, please. So how do we enable these rich operating system workloads on the drive? So really what we want to do is we want to have that rich operating system in there to take advantage of the tools and the ecosystem that's out there with Linux. The diagram on the left is showing an ordinary SSD today, or a typical SSD, where you've got all the cores running in real time, and the data is pulled off the drive and sent to the host, just as we're familiar with today. With computational storage, shown over on the right-hand side, we've reallocated in this diagram a couple of the cores for running the rich operating system, the Linux, for doing that compute. And we can take that Linux and we can extract insight from the data right on the drive itself, and then send that insight back to the host. Of course, we can still send the data as well, but if we don't need to move the data, we get all the benefits that Neil previously mentioned in terms of reduced latency, reduced bandwidth, lower power, and that clearly is what we really need here and really want in terms of extracting the insight from the drive contents. So how do we design a flexible controller with the Cortex-R82? Well, since it has the ability to run real-time and Linux, we can implement both of these solutions with the exact same set of cores, the exact same architecture. So we can do the classic enterprise drive where we've got all 4 cores in this diagram on the left running in real time, or we can take that exact same controller and say, well, we're going to use 2 of those Cortex-R82 cores and run Linux on them, and the other 2 will continue to serve as running real time for managing the FTL. And the beautiful thing about it is you have the flexibility to change the balance of the workload based upon the demands of the drive. So maybe, or the demands of the system for that matter. So perhaps during the day, the drive is especially busy in ingesting lots of data, and you can allocate maybe only 1 core for doing the computation at that time. Maybe it's so busy, aren't able to allocate any cores that are all needed for running real time. But then later on in the day, maybe the workload slows down, the drive has some more idle cycles. You can reallocate those same Cortex-R82s on the fly dynamically through software, reboot them into Linux, and begin using 3 cores now for doing compute and 1 core for running real time to get the data off the drive for the computation functions. All right, so with that, I'm going to turn it back over to Neil to continue discussing what's driving the adoption of Linux.
Great, thank you, Jason. So really, one of the big benefits that having Linux on the drive brings is that there's a huge ecosystem of Linux developers out there. So being able to take a workload that today runs on a server and move it directly to the drive where the storage and the data resides, I think is a huge benefit. And I touched on earlier, something like programming an FPGA, that's really hard. There's not many people that can do it, but there's this huge world of open source tools and software technologies and protocols, all that can just be moved directly now onto the drive to run on that data. So obviously with the ARM ecosystem for Linux, basically there's this cloud native software that's been out there. It's been ported and optimized to run really well on ARM processors, including the Cortex-R82. And it's this familiarity with these tools and technologies that I believe is going to really accelerate innovation and deployment. If you can quickly and easily develop workloads that can run on the data in the same way as you're used to doing, it's the same as before. So it's going to drive adoption, and I think it's going to create some really useful and interesting and exciting applications that can be done directly on that data. So really, to fit into this whole structure, the software-defined system is the trend. And what we mean by software-defined in this context is really about functions or workloads being isolated from the hardware that they're running on. So be that x86 or some other language, be it a server or be it on the drive. If you could isolate that high-level workload from the hardware through a hardware abstraction layer, this just makes it much easier to do that movement of workloads to where it's best suited to run. Obviously, this cloud-native, service-orientated architecture software is going to be very key to this, just to make sure that those functions and workloads can be moved and published and available and updated very, very quickly in the same way as any other piece of that system that people currently use. Basically, the computational storage drive now just becomes another extension of that existing system. So at ARM, we see this as very, very key. So we're developing Project Cassini. This is an initiative that really to ensure this cloud-native software experience works everything from cores that are running deep in the data center out to the edge, but also, of course, in the computational storage drive. So this is really designed to support a diverse range of ARM-based hardware and really leverage that ecosystem that things can just be moved around to where they're best suited to run. So Project Cassini is really made up of, it's focused very much on standards. So really how to create robust standards for software development, but also to enable different hardware solutions, innovation out there as well. We're not trying to paint everyone into a corner. This is all about enabling diversity and enabling innovation. But in order to build on that, you do need basically foundations for the security and certification so that people can trust that these workloads and ecosystems are reliable and secure. And also as part of this, ARM will be developing cloud-native software stacks and reference use cases. And this is really going to help this roll out across the entire value chain. So choice of different hardware, different performance points, different memory capacities from ODMs and OEMs, and enable everybody to really get involved and use an environment that's consistent. And this is going to reduce cost, it's going to reduce friction, and really make, I think, everybody's lives a lot easier. If you'd like to learn more about Project Cassini, the ARM Developers Summit, Dev Summit, is coming up on October the 6th to the 8th, again virtually. So please do, if you want to learn more, please do attend. I think one of the key concepts here as well that has probably become apparent to you as we've gone through this presentation is that here in the diagram on the left, it's basically a computational storage drive, and with an Ethernet interface it looks and behaves and acts just like an edge server. So it's got compute, it's got RAM, and it's got storage, and it's connected via Ethernet. If you look at the classic edge server on the right hand side, it's the same. It's just the storage in there requires, you know, the PCIe interface. You've basically got a bigger box with an SSD inside it as well as the compute, and you're not sharing that RAM as efficiently. So really a computational storage drive with an Ethernet interface is going to be a very, very low cost edge server. It's RAM, it's compute, and it's connected. So with the storage. So to me, that's a really exciting, and I can see lots of innovation happening there. Because of the volumes that storage devices are developed in, it's going to be really a very, very low cost solution. It could even be powered over Ethernet, so just one cable going into this box, and now you can have Basic is computational storage, and it can be complex with things like machine learning or other accelerators in that device to really get very good performance from that system. So that bit to me is really exciting as we move forward. So what are the key workloads? And there are really thousands, but I've chosen a few here. But in order to leverage the ARM cloud native software ecosystem, obviously we've got all of the operating systems, the major operating systems are supported. We have networking, we have all of the containers and virtualization, not just ported, but optimized and proven to run very well on this ARM ecosystem. Obviously the languages as well, and also all the workloads from things like TensorFlow for ML, but databases, many other areas. So things that can run well on ARM-based machines in the data center can now run equally well on the drive that's also in that data center or remote. So yeah, this is just really picking up this ecosystem, which is very, very important for the development environment. So in terms of migrating Linux workloads to these computational storage drives, as I mentioned, there are a huge number of workloads that exist for computational storage and where computational storage can really bring value. Some of them are fairly simple, like offload. So this is really where today, if you want to do compression of data that's stored on a drive, typically you would move that data to a server, you'd compress it, and then you move it back again. But some of these offload functions for encryption, deduplication, encoding, basically, they can all just happen on the data. So the drive can do that autonomously in the background. And I think that's very powerful, these kind of self-managing drives, but with these low-level functions. And to get really great performance, they may use hardware acceleration, but it's basically just offload for lots of the sort of common tasks, erasure coding. There are many, many that could be implemented. Another key one is database accelerations. Obviously, database is a classic example where you've got huge amounts of data that's stored, and in order, say, to search through it, you have to move all of that data to a server to look through it. Now, it'd be much better, obviously, to send a search request to the drive. It will return just the results. So you're really reducing the bandwidth requirements, the data movement in database acceleration. AI and machine learning, obviously they've got huge amounts of data, but the functions that actually run are typically fairly straightforward. You end up typically with some MAC, the multiply and accumulate commands that run at the low level. And as Jason indicated, Neon, the wide SIMD that we have in the A series, but also in Cortex-R82, that really accelerates machine learning workloads. So this enables you to do the machine learning directly where that data is stored. And you could be categorizing images for facial recognition or for whatever other ML task that you can think of. Obviously, I think the idea that for content delivery networks, again, if you have to convert to different screen sizes or different formats of data, if these content delivery networks can do that directly on the data where it's stored, and potentially storing that right at the edge of these systems, so it doesn't have to be in a data center somewhere. Actually, you can move it anywhere so that it's near where that data is actually going to be accessed. So for example, if there's a 5G tower with high definition mapping, you can put the tile around that mast to have that high definition mapping locally, which I think is really exciting. Obviously, SmartNICs are gaining great traction for doing offload from the main servers to the SmartNIC. What's exciting here is, as well, is that SmartNIC could then do additional offload actually directly to the drive itself. I think we touched on edge computing, this image classification and video, transportation as well, in everything from autonomous cars. Also, we hear in commercial aircraft where they're storing huge amounts of telemetry data in every flight, but actually those are typically removed and then the data is uploaded to be worked on when the plane lands. So there's a big delay before any insight comes from that data. With a computational storage drive, it could be monitoring for anomalies basically while the flight's in the air, and certainly notify people as soon as that plane touches down. But custom workloads, I'm sure there are many, many out there, but some of the workloads might be quite trivial. Today, a lot of SSD manufacturers have to customize drives for specific large customers, and some of the things they need to do are just really fairly simple admin functions of, what's the lifespan of that drive, what's the error rate on that drive, and they can report those off to a system in the server. But that's complicated to have custom workloads for specific customers. If their customer could develop their own workloads and modify it very, very easily, it's really exciting. It gives the big customers the ability to do whatever they want on the drive in a sandbox that's isolated from the firmware, and it removes one of the headaches from the drive manufacturers as well. But here are just a few examples. There are many, many others. So obviously, if you've got a computational storage drive, how do you get your workload onto that drive? Now, clearly, this is what the SNIA Computational Storage Technical Working Group is looking to standardize. So here over NVMe or NVMe over Fabric, there will be standards that enable this exact ability to create and download and manage workloads that are on that drive. But obviously, I think if you do have this TCP/IP link to the drive and you're running Linux, actually you can just take advantage of all the standard approaches that are used elsewhere in the data center, Kubernetes, Docker, many of the others out there as well. But in other cases, people may want to do things like the enhanced Berkeley packet filters, where this is a kind of a virtual machine that's on the system running under Linux that is a just-in-time compiler. So again, you can put down smaller workloads and manage those directly on the drive. But yeah, this is just the start. There could be many, many other ideas as well that fit in with the systems that are being developed. So here, just as a couple of examples, it's here we're talking about creating a more energy efficient Hadoop cluster. So in the diagram here on the left, we're really showing just a traditional Hadoop cluster where you've got the master node with processing and RAM, you're networked out to the data nodes, where again, you've got CPU and RAM for the data node attached to storage. Now here on the right, what we're showing is the same thing, but now actually inside the storage in that CSD data node, you can actually have the compute running there. So again, here we're showing the standard sort of SSD NVMe capabilities, but alongside it, you can be running Linux, Docker, JVM, the Hadoop data node, and the node manager in this container on the system. And that can be updated or changed using all of the standard systems. So yeah, this is one example. The second example, I was just going to go into a little more detail about doing ML and AI directly on the workload. So basically edge analytics with very, very low latency. So here it's fitting into a Kubernetes system where you've got the Kubernetes master, you've got the workers, but then you've now also got the computational storage drive, Kubernetes worker. And again, you can see as before, we've got the standard drive functions that are required here, but now you can also download AI ML workloads using Docker and do your edge analytics workload. And this all kind of fits in through that software stack that I was talking about, where we've got the ARM compute library that can then rely on Neon, but it's integrated with all of the leading AI and ML applications and frameworks to make sure that all works seamlessly. So, thank you for sticking with us this far. In the conclusion, really, I think computational storage is going to be very diverse. There are a huge number of use cases and applications out there, many of which people haven't even thought of yet. But actually, by putting Linux on the drive, and I think what Jason demonstrated, it isn't a really crazy idea. You've got the compute, you've got the RAM, and you've got the storage. It makes a lot of sense to have that Linux there. And that brings in that whole developer community, which is what is going to enable all of this innovation and this movement from the sort of compute-centric world to a data-centric world. So I think that's really exciting. These computational storage controllers, though, they're going to require flexibility. I think Jason demonstrated that very, very clearly, that If for every different generation of computational storage, every computational storage product, you had to size the amount of compute in there for real-time versus Linux processing, you could end up with a lot of different tape outs that are expensive. So, with something like the Cortex R82, that gives you the flexibility to make a controller that's really flexible. So there you can have one product, your next generation enterprise storage controller you develop using Cortex R82. It can all run real time, but you can then make another product using that controller where you've got Linux enabled on one or more cores, or even dynamically balancing that while it's running. So that flexibility, I think, is what's going to accelerate this market, enabling you to take an existing enterprise storage controller and now enable your customers to experiment with computational storage. Okay, well, thank you. Obviously, if you have any questions, please just reach out to us. And thank you very much indeed for joining us for this session today.